Hey everybody, I want to show you how to do linear regression. So we're going to do an actual example and not just talk about it this time. So let's get started. Let me share up the notes and I'll show you the example we're going to do. I have done something not great with this worksheet. I don't know why I wrote it this way, but I kind of outlined the example, how to do all of the stuff before I actually gave the example. So we'll give the example, then we'll go back. But first, let me talk a little bit about scatter plots. Scatter plots are pretty straightforward. They are plots of points. That's literally it. There's nothing else to it. You just plot the x's and y's. So if you remember, linear regression is all about bivariate data, right? Each point represents one particular like item or object. It's two things about that one particular item or person or whatever thing you're graphing here. And so there's two things about that. So you have an x and a y for each point, and you graph that, right? That's all it is. Like you decide what's going on the x and what's going on the y. And remember, if you recall from last video, y is the response variable. That's the thing that you are interested in tracking or predicting or whatever, usually based on x. And x is the independent variable that we're thinking of determines y. It's the explanatory variable. So whichever one of those whichever way you think the causation is going, graph them that way, but keep in mind that correlation is not causation. So you might actually have the causality wrong or backwards, or there might actually not be one. We'll worry about that a little bit later though. So scatter plots are basically plots of points, and they have different types of correlation, as we mentioned last time in the intro video. And so you can see a couple examples here. So there's a pretty clear linear trend among these points right here. Similarly, there's a pretty clear linear trend among these points. However, these points are more like a line, right? They're straighter and they're more tightly clustered around the line, around what the trend line would be. These are actually, it's still pretty clear in this case, but these are a little bit more loose around the line. And so we say these points are more strongly correlated. That is to say, X does a better job of determining Y, right? Here, X and Y are certainly still related, at least it looks like that from the data, but Y is not determined exclusively by X, right? X is not, it's not a deterministic relationship, whereas here it almost is, right? Here, so for this particular X of like, what is that, 4? Of 4, it looks like you could have a pretty wide range of Y values, whereas there's the same thing over here, right? If I look at X equals 4, I don't get a very wide range of Y values. So here the correlation is pretty strong, but not completely perfect. This one is almost perfect. The relationship here is incredibly strong. There are other kinds of correlation as well that we are not going to be worrying about. So the other types of correlation might be something like this. There's a pretty clear correlation here, but it's probably not linear, right? This pattern right here is not a straight line. It looks more like a parabola, or more likely an exponential function. And so we wouldn't necessarily want to do linear regression on this data because the trend is not linear, right? So we'll see a little bit later how to determine if there is a relationship between X and Y, or if we think we'll do a test called it's a t-test to see if there's a relationship between X and Y. And if we did that on this, the test would come back telling us that there is a relationship. And that's actually not exactly right, because there is a relationship, and this data, if we graphed a line, like a straight line that captured the trend, would do something like this, and it would actually be a pretty good fit. But the test isn't capturing the pattern here. It's just doing an analysis of how far away from the line are all the points, and does that make us think that there's a relationship. And in this case, the points would be relatively close to the line in aggregate, but there's a pattern that's not a straight line that the test wouldn't really capture. So you have to graph your line. You really need to graph it and check to see if there's an obvious pattern. And I'll show you a way to do that a little bit later. I don't think it's in the notes. It's called the residual plot. But the idea is that you want to be able to look for patterns to see if your data, if you're using the right model, essentially. Remember that linear regression is a model. It's supposed to be the model for how X determines Y, or how Y is predicted by X. And so if you're using the wrong shape of line, or the wrong shape of curve, that's bad, because you're missing the relationship there, right? So you want to look for patterns, and you want those patterns to be pretty straight, like these guys, right? Those are the trend is pretty straight. There's no, I understand this is a bit more of an oval, but the trend itself, as X goes up, Y goes up fairly constantly. The pattern that we're going to be most interested in, or the second most interested in after a straight line, is no pattern, right? So there's not a trend here, right? We can do linear regression on this, and we will get a trend line. We will get the best fitting line. You can always, no matter what set of points you have, you can always find whatever, you can always find the line that fits them best. You can also find other shapes that fit them best, exponential functions, polynomials, etc. We're just going to be doing lines. So we can find the line that fits this best, but when you look at it, it's pretty clear that X doesn't seem to have any effect on Y, right? So when I look at the X's here, you know, they're in this range, or excuse me, when I look at the X's, say around here, the Y's are in this range, and when I look at the X's over here, the Y's are in the same range, right? So changing the range of X's I'm looking at didn't really seem to have any effect on the Y's. Therefore, X is not a good predictor of Y, right? Changing X doesn't change what we're estimating for Y, so therefore there's probably not a relationship between the two. And so you don't want to do linear regression on this. And I'll go off on a small tangent here, so you can come back in a couple minutes if you don't want to hear my tangent. But the tangent goes like this: if you have data where there is no relationship between X and Y, you should probably not do linear regression. Not just because the model won't mean anything, right? You can always junk your own model if it doesn't mean anything. The problem is, lay people who read it and see that you have made a model will immediately think that that model means something, even if you tell them it doesn't. Even if what you tell them is, here's the model, and we do a little analysis and we find out, oh, this model doesn't work. They're not gonna listen to that. They're gonna think you did a thing, therefore here's a model, and we're gonna use that model, even if they shouldn't. So a bad model is worse than no model. When you do the T-test we're going to do a little bit later, or an F-test if you see it in another context, they're effectively they're doing the same thing. We'll discuss it later. But if you do a test and it determines that there is no relationship between X and Y, your analysis should probably end there, right? You should say there's no relationship between X and Y. X cannot effectively be used to predict Y. Analysis over. There you go. I mean, you might go on to say something like, this is interesting because we thought X was going to predict Y and then it didn't. So, you know, why is that? And then go into that. But don't say, here's the model we get when we do linear regression. And then, you know, 2 or 3 lines later, say something like, oh, it turns out there's no relationship, because people who don't understand statistics will not listen to that. No matter how many times you tell them, you will not be able to convince them that to not use a model that you found. Believe me, I have tried. This is an actual problem. Don't run into it if you don't have to. So anyway, tangent over. All right, welcome back, everyone who skipped the tangent. So we want to figure out how to make the line, essentially, how to make our model. And so I'm going to show you a variety of ways. I'm going to show you 3 different computer programs that will do it: one on your calculator, one on Google Sheets, and one on Desmos, which I really like the one on Desmos a lot, to be honest. I think it's the most convenient of the 3. Calculator is going to be probably a little bit more familiar to you, and is pretty good. And then Sheets is, they make nice graphs, but it's, I don't know, man. The formatting is not what I would have liked. I'll just say that. So I'll show you how to do it on all three. You can choose whichever one you like. If you're gonna do it on, like, if you're gonna make a graph on your homework, for instance, and copy paste it into your homework, I would recommend Desmos. Desmos does a really nice job of that, although their copy paste function is not great. If you just want like a nice graph, I guess Sheets would be a good choice. But the analysis is inconvenient and unlabeled for some reason. I don't know why they don't do that. Anyway, let's go into, let's see what we're doing. So here's the idea. All right, so here's me showing you how to do it on your calculator. We'll come back to that, I promise. Here's the question. So this is one I mentioned last time, or I mentioned in the last video. I want to use my students' midterm exam averages to predict their performance on the final exam. Right? Seems like a reasonable thing to do. Go to midterm test, you're probably good at the final. So the table shows midterm averages and final exam scores from 2 previous stats classes that I've aggregated together. Yeah, and people always get messed up by this. So this is one table. I know it's 2 rows, but I just ran out of room. I could cram it small enough to fit on one, but it was really hard to read. So it's 2 rows, right? So we got the midterm averages of the top rows, and then the final averages of the final exam scores are the bottom rows, right? So midterm averages are all of this stuff, and also all of this stuff, right? So that's what it's not. Sorry, like I said, my mouse has been going down on me. Anyway, these rows are the midterm averages, and then the bottom rows are the final exam scores. So what I'm going to do is I'm going to type those into the calculator. As you can see, I have done up here, right? I'm going to put my x's in L1 and my y's in L2, like this. I'm going to go ahead and pause the recording and do that. And I would strongly encourage you to do the same and, type along with me, essentially. Just like I've said many times, actually doing stuff while you're learning is really helpful. So yeah, I'm going to do that. So let me just start this off. Oh my God, what's happening here? Sorry, I forgot I can't expand all the way, or my computer will not let me grab my toolbar. I don't know why it puts my toolbar behind things. All right, so anyway, here's what we're going to do. We're going to go over to the calculator, and we're going to go to stat and edit, and I'm going to put them in L1 and L2. You don't have to watch me do all this, so I'll go ahead and stop recording, and I'll pick back up when I've got it all typed in. All right, I've got it all typed in. Let's share up my calculator. So as you can see, I've got this all typed in. So here's what we're going to do in order to do linear regression. So actually, let's go back to the questions real quick, and we'll answer them. Where am I at here? There we go. All right. So here's my my question and data. Which of the variables should be X and which should be Y? So again, we want to think about what we're trying to predict and what we're trying to base that prediction on. The thing that we're trying to predict, and in this case, is the final exam score based on somebody's midterm average, right? And we're not doing it for these classes. We are using these classes to predict other people's scores would be the idea, right? That's the model that we're building here, using the data from these guys. So I want my X's to be my midterm averages and my Y's to be the final exam score, right? The soon to be predicted score. Now we have some relationships that we talked about. Oh, I don't know if I actually called them anything up here. So let me scroll back up here. So we have 4 different relationships that I talked about. I don't think I necessarily mentioned the difference between these guys. These are both linear, right? Pretty clear linear trend down, linear trend up. We call this a negative linear trend, this guy right here, and this one a positive linear trend, because we are thinking that in each case, a positive change in X results in a negative change in Y, whereas here, a positive change in X results in a positive change in Y. And so it's that negative change in Y versus positive change in Y that gives us negative versus positive. It's also the sign of the slope of the line, right? So here the line has a negative slope, and here the line has a positive slope. The trend line has a positive slope. And so we call this a negative linear relationship and this one a positive linear relationship. And if you're looking for adjectives to describe how strong the relationship is, this linear relationship is incredibly strong. This one is reasonably strong, right? This is medium strong here. By that I mean that, like, how correlated are these? And we'll talk about a way to quantify that in a little bit. But right now we just want to make the line. This one I would describe as nonlinear, right? There's a relationship, but it's nonlinear, so I would say that's a nonlinear relationship. And this one I would say there is no relationship or no correlation between x and y. So when I'm asking about the kind of relationship, that's what I mean. I'm expecting to see, well, let me pause for a second and let you think about what kind you'd expect to see, and then we'll talk about it. So I am expecting to see a positive relationship, probably a positive linear relationship between these. The way you want to think of them is a positive relationship means that an increase in one results in an increase in the other. Negative relationship is an increase in one results in a decrease in the other. So for instance, something that might have a negative relationship would be like, let's say you run cross country, and then the more you practice, the lower your times get, right? So the faster you go. So I'm thinking of an increase in practice time results in a decrease in race time, right? Or how long it takes you to run your 5K or whatever you're running. Positive relationship is something that reinforces something else. So the more time you study, the better you will do in a class, or the better you do on your midterm, the better I would expect you would do on final exam scores. So I'm thinking of this as probably a positive relationship. And of course, I'm cheating a little bit because I've already done this analysis, and it is, but that's the logic you want to use there. I'm not expecting a none relationship, or I'm not expecting no relationship. I'm thinking that midterm average probably will predict final exam score. And nonlinear is a possibility here, right? It's possible that there's some weird nonlinear relationship here, but most things that are related to each other have a linear relationship. I don't want to say most, a lot. It's the most common one. A plurality of things that are related have a linear relationship, I would say. So I'm expecting to see a positive linear relationship, but I wouldn't be shocked by a nonlinear relationship. I would be shocked by a none or negative relationship. So put the x's into L1 and the y's into L2. Of course, I've done that. And then we're going to make a scatter plot. So I'm going to show you how to make a scatter plot. We're going to go through and do all this on the calculator. Then I'll show you how to do the same stuff on sheets. So on sheets and in Desmos. So as you can see, I've got all my data in here. X is in L1, Y is in L2. You can put them in other columns if you want to, or in other lists. But the default is L1, L2. And then we're going to do linear regression. And so there are at least 3 different ways I know of on your calculator to do linear regression. We're going to do the most complicated kind. It's not that complicated. It's just a couple extra button presses. But it also gives us a lot more information, some of which we're going to want. So I'm going to go ahead and quit out of here, and then I'm going to go to stat, tests, and Linreg T-Test, which is way at the bottom here. So way down at F. Oh, and by the way, in case you didn't know, if you hit up when you're at the top of the list, it'll go to the bottom of the list. Like, it'll wrap around like Pac-Man style. I don't even know if you guys get that reference, but that's it'll wrap around. So I'm going to go do Linreg T-Test, and it's going to give us a little bit of stuff to input here. There's a couple things you can do. So you can change the X and Y list, of course, but I of course put my X's in L1 and my Y's in L2, just like I recommended you do. Leave this on not equal to, and we will talk about what this means. It looks like a B and P, but fancy. These are Greek letters. This is beta and rho. This is actually a Greek R, not a P. We'll talk about what that means a little bit later. In fact, if you look just below where we're at in the notes, it says measures of correlation. And that's where we discuss rho, and then a little bit lower, like what these things are. Now, remember, I mentioned that we're going to do a test to see if there is a statistically significant correlation between X and Y. That's this. It's asking for the alternative hypothesis for that test. We're always going to want it to be not equal to, and I'll explain why when we get there. Then there's the calculate button, which we're going to get to in a second. this reg EQ this says regression equation. That's what it's asking for. And so what you want to do is put in a variable where it will store that. And I'll show you what I mean. So here's the idea. If you go to y equals, now you don't have to go to y equals when you do this, but notice that we've got y1, y2, y3, etc. So what I'm going to do is I'm going to put in y1 into reg EQ. So let me go back to that real quick. I'm going to put y1 into reg EQ, and then what it will do is it will store the equation that it makes into y1, and then we just have it in there. The other option, you don't actually have to fill this in. You can just say calculate and then write it down and then type it in if you want to. But this is simpler. This is a few button presses though, so you might want to watch this a couple times to do it. So here's what I'm going to do. I'm going to go to variables, not distributions. Right? We've been doing second vars to get to everything, but we don't want distributions. We want variables this time because I want a y variable, and I want a y variable. So I'm going to go here. And the thing I want is a function. So I want number 1 here. And then I can choose from all those variables that I showed you. I'm going to choose y1. You can choose any of them that you want, and it'll store it in whichever one you say. So I'm going to hit enter on y1 or just hit 1. And there you go. It made a y1. And then I'm going to hit calculate, and the screen is going to fill up with stuff. All right. So there's a bunch of stuff here. We want almost none of it right now. We will learn about all of it. I'm not really going to talk about the degrees of freedom, but this is the degrees of freedom for the t-test I mentioned. And this is their p-value, and this p-value right here is for the test as well. So we'll talk about this in a little bit. The thing we care about is A and B, these two things right here, because the function or the equation that it is making, remember we're trying to make a linear equation here to model our data, is y equals a plus bx, where a is this 6.41 and b is 0.947, right? So these are the coefficients in this equation, right? So it's y equals 6.41 plus 0.947x, right? That's the equation of our line. And if we go to y equals now, oh, and by the way, if you leave this screen, you will have to run the test again every single time. A little irritating. So we're probably going to run this like 6 more times, just in the context of this example. But I want to show you this. So if I go to y equals, notice that it has stored the line in there as advertised, right? This was A, 6.41, and then B was 0.947, right? And it stores it to 10 decimal places, which is a little irritating, but it's, hyper accurate. And there's an X over here that you can't, that's just off the screen. So it's A plus BX. And so it made the line. Now I would also like to be able to graph the points that we put in, right? So I'm going to turn plot 1 on. First, I'm going to check to make sure that plot 1 is a scatter plot. So I'm going to go to stat plot here, the second function of y equals. And this is the symbol for a scatter plot, which this is the default. And I of course, just turned on a fresh calculator every time. This time, like every time. So this is what I want. So that's good. I'm going to go back to y equals and turn on plot 1 by highlighting it and hitting enter. And now it's on. So notice that I'm graphing both the points and also the line. So I'm gonna graph that all together. So let's go ahead and hit graph, and it's not going to show us the points because we're not zoomed properly. Remember, we have to hit zoom stat. So we're going to go to zoom and number 9, zoom stat. There we go. And so I've graphed the points and the line. And that does indeed look like the trend line. And the trend does in fact look linear, right? Like if I were to go graph it without the line. So here, I don't know if you guys knew this, but you can turn your lines off in your calculator. You can turn your functions off by moving over the equal sign and hitting enter. Notice it's not highlighted now. And so it won't try to graph the line, or it won't try to graph this function here. So if I just hit graph, it'll just show the points. This is a pretty clear linear trend, right? Not super clustered around the line, but an obvious linear trend, right? And if you're not clear on just looking at a bunch of points and saying, is that trend linear? The thing you can do is look at the left side of the graph, see where the points are. Look at the right side of the graph, see where the points are. Was there an obvious pattern, right? If we look at the left side here, that's way down low. And if we look at the right side here, that's way up high, which is kind of the pattern we were expecting to see in the first place. So that sort of confirms my theory that this is that there's going to be a reasonable linear trend, right? This trend is linear. There's a couple points that don't necessarily exactly fit that. Like this guy is kind of wonky and far away from the other ones, and so is this one. But we'll discuss those in a little bit. So I'm comfortable with this being a linear trend. So we're going to go back and turn this on. Grab that. And the line does indeed fit the data pretty well, right? The data is pretty linear. So there we go. We found the equation of the line that fits our data the best, and now we're going to do a little bit of analysis. So let's flip back to the notes and see what other questions I asked. Okay, so make a scatter plot and check to see if there's a linear relationship, right? Yeah, there was a linear relationship. So Linreg T-Test, that's the thing that we did in the calculator. You go to stat tests all the way to the bottom to Linreg T-Test, and it'll find this for you along with a bunch of other information that we're going to use in a bit. So here's what I want to do. I want you to be able to interpret what the picture is telling you, essentially. So I've got student number 2 and student number 5. So let me show you around the scatter plot a little bit. So let me go back to, whoops, where am I at there? Let me go back to here. And so we can see a bunch of dots and a line, right? And that's what we were expecting to see. One nice thing that your calculator does is if you hit trace, this guy right here, right next to graph, it will go over the points and over the line. So one thing to notice is it's starting in the upper right. That's not like normal. What it does is it starts at the top of the list. So like if you, here, let me go to the list here. So stat, edit. So that first point was 96,100, and the second one was 78,90, then 57,62, right? And if you've got the notes open, you can see all the other ones too. And so if I go back to the graph and hit trace again, the first one is 96,100, and then I'm going to hit right. I'm going to hit the right arrow key, and it's going to move down the list. So I hit right, and it goes to the second one on the list, which was 78,90, and I hit right again, it goes to the third one on the list, which was 57,62, as I said. So if I want the second person in the list, there's the second person, right? 78,90. There's the first person. So it's going to look like it's jumping all over randomly, but it's not. It's actually going down the list that we put in. So if I hit right, switches point to point to point to point. And you might say, well, why not just hit up and down, right? Why wouldn't down move down the list? Up and down switch functions. So if you go and look in y equals, up at the top here, we've got the plots, and then going down the list, we could have other functions in here. And so what it does is if I hit down or up, if I hit down, it will go down that list of functions. It'll start with the points. Notice that it's doing plot 1 here first. And if I hit down, it switches to the next thing down the y list, which is the function, right? That was the line that we got here. And now it's tracing along the line. And so you can hit right and left to move along the line. So left moves you left, right moves you right, etc. And if you hit down again, there's nothing else to switch to, so it'll jump back to the top, just like it does in any of the other lists in the calculator. So that's how I can show you around this a little bit. And the question I asked on the notes was, what about person number 2 versus person number 5, right? So student number 2 was this person right here. The question is, did this person do better or worse than we expected? And the thing you want to remember about regression is the thing we expected is the line, right? So the line here is our prediction for what anybody would get. Now, we're aware that that's not the actual final exam score that anybody's going to score, right? None of these actually fall on the line. I know a couple of them kind of look like they do. They're just very close, and the calculator has low resolution. So none of these people actually fall right on the line, but that's our expected value for a given x, our expected y for a given x value. That's what we're thinking of the line as. So our expectation is that the person who scored 78 would score about here, and we'll see how to find that prediction in a little bit, or get an exact number for that. And they actually scored up here. So their y value, which is to say their final exam, was higher than we thought it would be. So they did better than we expected, and that's great. This person did nicely, or this person, outperformed our expectations. And I go to person number 5, so 2, 3, 4, 5. This person right here was a little bit under the line, so their performance was a little bit worse than we thought it would be, or their score was a little bit lower, right? Now their score was still good, y equals 89, right? You got 89 on the final, nothing wrong with that. But we thought they were going to do even better than that based on our prediction. So you can tell whether a data point was higher or lower than expectation based on where it is relative to the line, right? Above means higher than expected, and below means lower than expected. Keep in mind that higher doesn't always mean better, and lower doesn't always mean worse. It does in this context, but if your context was like cross-country race times, right, higher would be worse and lower would be better. So it depends on what you're doing, whether higher or lower means better or worse, but you don't even really need to think of it in terms of better or worse. Just think of it as this person did higher than we thought, or this data point was higher than we thought it would be, that one was lower than we thought it would be. That's it. Switch back to see what else we asked. Switch back here. All right, so from our scatter plot, student number 2 scored a little higher than we thought. Student number 5 scored a little bit lower. So I want to talk about what residuals are. So residuals are the numerical value of that thing we were just talking about, of was this data point higher or lower than expectation. So a residual is just the vertical distance from the point to the line, right? How far away is this point from the line? So let's see how we can calculate that. Now, yeah, let me go back over here. So the way we want to think of this is we want to see what was this data value relative to the line, and I would like positive residuals to correspond with being above the line, positive numbers being meaning that this was higher than we expected, and negative residuals to correspond with being below the line, like this guy or this guy, right? So below the line should be negative residuals. And so what I want to do is I want to subtract our y value, the actual y value of the data point, minus the value of the prediction, so that we get a positive number if the y value was bigger than the line, or bigger than the prediction. Oh, excuse me, I'm going to sneeze. Oh. Sorry. Okay. I apologize. So we get a positive residual if the y value was, if the y value of our point is bigger than the y value on the line, and a negative residual if the y value of the point is smaller than the y value on the line. So let's go to a whiteboard, and I'm going to talk about how we're going to do that. So I'm going to let y equals data value. I'm actually y sub I is the data value. So this is the ith y value. So for instance, we have in this set of data, we've got 29 different y values. So y1 is the first one, and y2 is the second one in the list, and y3 is the third one in the list, etc. And then y sub I hat actually equals predicted y value. So what we have here is we have two different kinds of y's, right? This one is this one is for the line, and then this one is for the actual data values. So I want to reserve just y for data values and y hat for predicted y values. So what we actually have in our line is this. We actually have y hat equals a plus bx. So y hat is our predicted line, and then a and b were the things that our calculator found. So our residuals are going to be y minus y hat, our actual value for the point minus our predicted value, right? And there's a letter for residuals. It's an epsilon, or some people use e's. Yeah, so I'm going to use epsilon. Your book uses epsilon, so I'll use that one. So epsilon is like a fancy e. So e sub I equals yi minus yi hat. This says the residual equals the actual y value for the data point minus the predicted y value for the data, predicted y value for that point. Right. So this is our formula for residuals. Now our calculator is going to do all this automatically. It's actually relatively easy to do this by hand if you want in the lists. But there's just a function in it that for your calculator that makes it really convenient. But that's what we're doing here. So a residual here is just the difference between the actual y value and the predicted y value. So let's go back to the calculator and see how we can find these. So yeah, so if I go to stat edit, so here's my my points, right? So these are the actual y values. So these guys right here are all of the y's, not the y hats. These are y's, right? These are x's. Those are not in this calculation. So if I want the predicted values, what I can do is I can put in the x value into the function that we made, and it'll give me a y value. But I'm not going to do that. Your calculator will do all that for you automatically with the resid function, which finds residuals. So I'm going to go up into the header of L3 here. So again, not in the main column, I'm up in the header. And then I'm going to go to list, not stat, but the second function of stat, which is list. And resid is the thing you're looking for. That, of course, stands for residuals. And if I just put resid in here, it'll find them all for me. Right, so this 2.7067, this is saying that this is a positive 2.7. So this is saying that this person, the first one in the list, scored 2.7 points higher on the final than we would have predicted based on their midterm score. That's what this says. So let's look at the graph and we'll be able to see it. So that is the first person. So trace here, left until we get back to the first person. There we go. So here's the first person in the list. They actually scored 100 on the final. That is 2.7 points higher than we thought, or higher than what our prediction is. And as you can see, this is very slightly higher than the line. Now, if we go look at, let's see here, this person, right? So this person that we were talking about, person number 2, they scored more above the line, right? So their final score exceeded our prediction by more. So let's go see what their residual is. Right, so the second person has a residual of 9.7, so a bigger number, right, farther above the line. And if we go down a little bit farther, like person number 5 here, as we noticed, they scored a little bit lower on the final than we thought they would, about 4.5 points actually, right? And that was the person that we saw from the example. We can see some other ones, right? This person is way below the line, scored 25.5 points lower than we thought they would. And these are actual people from my stats classes. I don't remember who this is. This is several years ago, but they must have had a kind of a bad day on the final. So sorry to this person, whoever they are. Hope that I don't remember what their grade was, but I hope it worked out. But yeah, that's what you can tell from looking at the graph how people did relative to our predictions, and we can use our predictions, our predicting power, to take this data and extrapolate it to new people who are not in our data set, right? Like, so for instance, I might use this model that we've created here, this one right here, to say predict a student's final score. Now, I will say this, I wouldn't use this model because for a variety of reasons. So one, you don't want to go telling students, here's what I think you're going to do on the final. No, because like that, it's not determined, it's not predetermined, right? Anybody can do much better on the final or much worse, depending on the effort they put in. So that's my message to you. You want to do well in the final, put in the effort, it'll work. But let's say I wanted to do some sort of prediction. I could put somebody's midterm average in here and use this to guess what their final exam score would be. And that's in fact what linear regression is often used for. That's one of the things that you do with it. Yeah, so we'll talk about how to do that in just a second. Let's just go back and finish answering the questions for this problem. How do we describe the relationship between the regression line, data points, and whether one of the y's is higher or lower than we expected? That's what we were talking about. If the data point is above the line, that the y value is higher than we expected. The response variable was bigger, came out bigger than we thought it would in that case. If it's below the line, if the point's below the line, then the response variable came out lower than we thought it would for that point. Okay. Let's talk about how we can analyze our data. So remember that we got a bunch of information there. Aside from just the equation of the line, and I want to talk about what that information is telling us. So, measures of correlation. So remember up here, we mentioned that some data is more strongly correlated than others, right? So here I would say that X and Y, the variables, are more correlated than they are here, are more strongly correlated than they are here. This is roughly what we have with our test data, our exams and finals, our midterms and finals. This is more tightly correlated than that. Now we have numerical measures for that, called R and R squared. R is one of them, and then R squared is another one, or those are the letters. The correlation coefficient is R, and the coefficient of determination is R squared. And they do roughly the same thing, except R squared does a little bit, just a little bit more. And so in general, people usually use R squared to describe the strength of the relationship. And R is generally not used. I guess some people still use it. I usually see R squared. So R is always between -1 and 1, and closer to either end, either 1 or -1, is more correlated. So 0 is uncorrelated, and 1 or -1 is strongly correlated, like perfectly linear, actually. With the plus or minus sign just referring to the direction of the line, so that, or the direction of the relationship, I should say, right? Positive correlation or positive linear relationship is a positive number, and negative linear relationship is a negative number. But 1 and -1 have equal strength, just in opposite directions. Coefficient of determination is R squared, and this is not just like a name change from R to R squared. To find the coefficient of determination, you literally just square this. That's why it's R squared. It's literally just R but squared. So because squaring something gets rid of the sign, right? It always makes it positive. R squared is only between 0 and 1, with 0 meaning less correlated and 1 meaning more correlated. Yeah, that's that. The reason we use R squared in general is this down here. R squared gives you this kind of funny, I don't know, meaning, I guess, that it's a little hard to think about at first. But so what R squared is doing is it is finding how much of the variation in the y's is due to the relationship between X and Y, and how much of that variation is due to random other things. So for instance, too far. Here, the amount that the y's change is mostly due to the fact that they follow a linear trend. Whereas here, the amount that the y's change is somewhat due to the fact that they follow a linear trend, but also somewhat due to the fact that they're just kind of random and sort of all over the place. Like, for instance, if you visualize the line going here, right? So this point right here has a bigger y value than that point, even though this one has a bigger x value, right? So the change from this point to this point, there's a positive change along the trend line, but the actual change was negative. So there's some variation there from point to point. And it's not exactly clear what is causing that variation in the y's, right? We're only modeling the one thing. They're just the one variable for y. We're thinking of, or excuse me, the one variable that we're thinking of explaining y is x. But here, x increased, but y decreased, right? So why the change? Well, we don't know, right? It's something that's not x that's causing that change. So that is what R squared is telling you. R squared is giving you what percentage of the variation in the y's is due to the relationship between x and y, and what percentage is due to other stuff, like other stuff that's just not included in the model. So to put this in context, let's think of it in terms of test scores, right? So when you take a test, you take the final exam, some of how you do on the final exam is going to be predicted by how you've done on other tests previously, right? Presumably you did roughly the same preparation, and you understand statistics approximately equally as well. And we're thinking of midterm average there as sort of aggregating all of that stuff into one number. And then your output on the final exam is based on all that stuff, plus how you're feeling that day, and whether you just had a bunch of other finals and now you're taking my final and you're exhausted, right? And how much sleep you got, and how well you ate the previous day, how stressed out you are for whatever reason. So a whole bunch of other stuff that we're not accounting for, right? Our model only predicts final exam score based on midterm average, not based on how much sleep you got the previous night, or how much time you had to study for this final, or anything else, right? Literally just midterm average, that's all we're predicting. And so there's other factors that go into how well someone does in the final, aside from just how well they have done on previous tests. And so R squared gives you the percentage, a percentage version of how much of the change is due to the relationship between x and y. So how strongly final exam score is predicted by midterm exam score. And then how much of the variation in the y's is due to other factors that are not considered in the model. And so for us, when we do this here, let's go back to calculator, and we can see that we'll run that test again. As I mentioned, we'll be doing this a couple times. Linreg T Test, calculate. Okay, so you can see if I scroll down a little bit here, it gives us R and R squared, right? So R is 0.8768 and R squared is 0.7688. So notice that R is positive and the trend line, positive slope as expected. R squared is 0.7688, or let's say 77%, or 76.9%. So about 76.9% of the variation in final exam scores is due to the relationship between final exam scores and midterm averages, and 23.1%, which is the rest of it up to 100, right? 100 minus 76.9 is 23.1. About 23.1% of the variation in the final exam scores is due to other things not considered in the model. This number is pretty high. This is, I would say, I don't know how to describe this, but usually some people use like 80% as a sort of unofficial cutoff for strong relationship. So this is right around where the cutoff is for a strong relationship between final exam score and midterm exam score, and midterm average. I would say this relationship is fairly strong. Very often people will use 20, 50, and 80%, something like that, or 20 and 80%. Anything below 20% is a weak relationship. 20 to 80% is moderately weak to moderately strong, and then above 80 is strong. Feel free to use those descriptive terms if you want. There's no official like mathematical basis for why people use those numbers. People just kind of agreed that those fit the descriptors relatively well. So feel free to use as you see fit. But bigger means stronger, right? Bigger percentage here means stronger relationship. And this is a pretty strong relationship, pretty strong linear relationship. So that's what R and R squared are measuring here. Now, a really important point that I want to mention here is, in general, you want to do a hypothesis test to see if there is a significant linear relationship between the variables. And so this is, I'll explain this test a little bit here, but basically what we're trying to do, what we're trying to determine is our data uncorrelated like this, or is it correlated like these guys, right? So is there actually a statistically discernible linear relationship of any kind in the data? And it's a little bit too complicated to get into how exactly the test is done, which is kind of fine for us because we're just gonna have the calculator do it anyway. Let's scroll down a little bit here. But that's what we want. That's what we want to find with Linreg T-Test. That's why the function that we're using is Linreg T-Test, is because the test that I'm talking about is the Linreg T-Test, right? It's the linear regression T-Test to see whether X is related to Y. Now, here are the hypotheses for the test. Now, this is going to take a little bit of explaining. So here's the explanation. I want to explain what beta and rho are. So this says the null hypothesis is that beta and rho equals 0, and the alternative is that beta and rho are not equal to 0. We always want to use not equal to, so there's no, we're not going to do greater than or less than. There's really no sense in it for this purpose, and I'll explain that in a little bit. I want to just explain rho first, but I think I'll explain what beta is. So if you remember, when we found our regression equation, let's flip back to the calculator. When we found our regression equation, we found A and B. Let's say we found the coefficients for the line based on our data. What that means is that A and B are numbers that were determined by our sample. That is to say, they are statistics, right? So A is what we determined to be the y-intercept of the line, and B is what we determined to be the slope of the line that we found. But the line that we found was all based on our data, so all of that stuff is statistics. What that means is there are parameters that are the equivalent of those statistics. A and B both have corresponding parameters. As is standard, we refer to our parameters with Greek letters and our statistics with English letters, or Arabic. I don't know. We use English letters for those. So the corresponding parameters for A and B are alpha and beta. And there's another one for R as well, right? So R is the correlation coefficient. And again, that is calculated based entirely on our sample. So this is a statistic. And there's a corresponding parameter called rho. That's what the rho is, or the Greek R is rho. So this number right here is testing, or is measuring how correlated our data is, right? And I know we used R squared, but R and R squared both test the same thing, or both measure the same thing, I should say. So this number right here, the bigger it is, the farther away from 0 it is, or the closer to 1 or -1, the more correlated our data is. And so the test that we're going to do is based on R. Is R far enough away from 0 that it makes us think that rho is not 0, right? So, and when I say, by the way, just to be clear about what I mean about a corresponding parameter, here's the idea. R measures how much of a straight line our data is, essentially, how correlated our data is, how correlated X and Y are. And that's based on these people right here, right? The people right here gave us an R. If we were to theoretically put every possible statistics student into this same box, right? Had them taught the same class, given the same tests, take all their midterm exam scores, all their final exam scores, and plotted them all, right? Every possible statistics student. The thing that we would get for our correlation coefficient would be rho, right? But we're only using a sample of them, so it's R. So the thing we really care about is rho 0? So is the population correlation coefficient 0 or not? So that is why our test has hypotheses that look like this, right? Don't worry about the beta for a second. I'll explain why beta equals 0 is equivalent in a little bit, but just concentrate on the rho for now, right? So we're just testing to see if rho is 0 or if rho is not 0, right? Those are what the hypotheses are that I'm thinking of right here. So 0 means, so R equals 0 or rho equals 0 means uncorrelated, right? That was this guy right here, right? This has correlation coefficient that's very near 0 because X and Y are not related, whereas these guys have correlation coefficients nearer to 1 or -1 because they are correlated. So that's the test that we're doing. What we're looking for here is if we cannot reject the null hypothesis, then our conclusion must be that the data is not correlated. So if when you do the linear regression t-test, the thing that you get is that you don't get a small enough p-value, then you should not pay any attention to the regression. You should throw it out essentially. So let's go back and look at Linreg T-Test again and see what we got. Now, I would argue that it's pretty clear that this is a fairly obvious trend. So I am expecting a pretty small p-value, right? This is a pretty obvious trend with a fair number of data points, 29 data points. And so I would expect a pretty small p-value. So if I go to stat tests, Linreg T-Test, as mentioned, we're doing this a few times. Notice that what we're doing here is this, right? This is the test that we're doing. We're testing to see whether rho is 0 or not, right? I don't care if it's positive or negative. I only care if it's 0, which means uncorrelated, versus not 0, which means correlated in some way. That's why we're leaving this on not equal to all the time. Calculate it, and my p-value is tiny, really, really, really tiny, right? 4.43 times 10 to the -10. So there are 9 zeros. There's a decimal place, then 9 zeros, and then 443. So that tells me that this p-value is tiny, and I want to reject my null hypothesis, which is sort of good, because that means that we think rho is not equal to 0, which is to say our X and Y are correlated, right? Small p-value means correlated. Big p-value means not correlated. That's the test that we're doing right now. The crash course video explains this reasonably well if you want to go look at that. I think I should have that posted in the module. So this is the screen I was looking at on my on the calculator, and there we go. 4.4 times 10 to the -10, absolutely tiny. So I want to explain why beta equals 0 means exactly the same thing as rho equals 0. So you don't technically need to know this, but I will go ahead and explain it anyway. So feel free to skip over this portion of the video if you would like to. All right, so here's my explanation of why beta equals 0 means exactly the same thing as rho equals 0. So here is, I'm going to do a whiteboard for this explanation. Give me a page. So here's my explanation. So let's say I have this data. X, Y. So the regression line gives you a predicted Y for any value of X. That's the way we want to think of it. So if I make the trend line is positive like this. Now, of course, this is not a good trend line for this. I'm not suggesting it is. But when the trend line looks like this, we are saying that as X gets bigger, we think Y is going to get bigger. That's not the case here. Here, the Y's are pretty much the same wherever you go X, Y's, right? So wherever you're traveling left to right, you get approximately the same y's. Maybe there's a very slight downward trend here. So what that means is the regression line will come out something like this. So when x and y are uncorrelated like this, what you get is the same prediction for y for every value of x, right? So this blue line here is our prediction for the y value based on what the x value is. And it's the same everywhere. That is to say that if we change x, our guess for y does not change. That means that y is not predicted by x, or x and y are uncorrelated, right? They're independent of each other. Y is independent of x, which is not what we want in linear regression. And notice what kind of line we got here. We got a horizontal line, which is one that has a slope of 0. So if you think back to algebra times, horizontal line means slope of 0. And beta is the population, it's the parameter slope, right? Remember, B is our sample slope, or our statistic slope, and beta is the corresponding parameter slope. So if the parameter or population regression line was drawn, it would have a slope of 0 if x and y are uncorrelated. So that's why we're testing to see if beta and rho are 0. They have the same meaning, right? I actually don't know which one your calculator does. There's actually 2 different tests, I believe, for this hypothesis test. I've never done this one by hand, so I actually don't know. I just do it on the calculator and let the calculator tell me. But that's the basic idea. So I think we're just testing R. Like the only tables I've ever seen for this are for the correlation coefficient, not for the slopes. But yeah, that's the idea. That's why it says beta comma rho equals 0 or not equal to 0. Is we're also testing beta at the same time by doing, like, what it's really saying is it true that the population regression slope, or the population slope, is 0, and that the population correlation coefficient is 0, because they're 0 at the same time. So as far as I know, they're just doing the test with R. I actually don't know what the test would be with beta, but we could figure it out, but I'm not going to worry about it. So that's why we get these null and alternative hypotheses. There you go. Okay. Tangent over, extra information over. Back to your regularly scheduled regression lecture. There are just 2 more things that I want to talk about with regression: interpolation and extrapolation, and outliers, how to calculate them. So yeah, so let's look at our graph again, so we can see interpolation and extrapolation. And then after all this, I'm going to show you how to do it all on sheets, and then I'm going to show you how to do it all on Desmos, which I like a little bit better. So interpolation and extrapolation. For those of you who are up on your Latin roots, I think these are Latin. These got to be Latin, right? Inter means inside, and extra means outside. So the idea of interpolation is you are estimating inside your data, inside the range of your data. So let's go back to the graph. Let's go right here. So within the bounds of our data, right? Our data goes from, this was something in the 40s up to like 96 or something like that, right? So in between those X values, we can be reasonably confident that our model is pretty good, right? Because it was created with things that were within those X values. Things outside of this are suspect. X values outside of this are suspect. Not necessarily wrong, but also not necessarily right either. So it's a little risky to estimate Y values, because remember, what we're doing with this model is we're estimating Y values based on X values. So if your input into the function is an X value that's not within this range, it's not necessarily clear that your Y value will mean anything. If you are close, right, if it's only a little bit above or only a little bit below your data, you're probably safe. If you're way far away, you're probably not safe. Trends don't necessarily hold for all values of X. And so let me give you an example of this. And this is just to re-emphasize just how critical it can be to use a model wrong, like how bad it can be. We are far enough away from 2008 now that a lot of you might not actually remember the financial crash of 2008, but I like that as an example here. So there's a lot of things that caused this crash, but one of the underlying factors was housing prices. Housing prices were going up. They just kind of kept going up for a long time. Basically roughly from the middle of the Clinton administration around 1994, 1995, something like that. Pretty much right up till 2008, they went up pretty much the whole time. That's a long time of going up. That's what, 15 years or something like that. So what people started doing, they noticed this trend, obviously, and there's kind of an obvious cause for why housing prices keep going up. You know, we run out of space and houses get more expensive because of lack of, you know, the land gets more expensive, and so you can kind of predict that housing prices are probably going to go up over time based on supply and demand. And so when people saw that that's what was happening, they just assumed that was going to continue to happen, right? And I don't know if you were old enough to know this at the time, but house flipping, buying a house, sprucing it up, reselling it, basically started to be a big thing around that. And people were thinking of houses, you know, having seen this trend, a lot of people were thinking of houses as investments more than like a box you live in, right? And consequently, a lot of people bought houses. And to buy a house, they're too expensive. Almost nobody can just, you know, write a check for a house. You got to get a loan. And so what ended up happening was the bank saw this trend, and I don't want to go into the details of why they made loans easier to get, but they did. So everybody saw this trend, real estate going up and up and up and up and up and up. And and people just kind of expected that to continue forever, right? And so they bought a house, assumed that it would go up in value and they could resell it for more. So they did some foolish things, like get a mortgage that is very cheap at first and very expensive after a period of time. And they just assumed they would sell the house before the mortgage became expensive and pay off the mortgage and never have the expensive thing happen. It's called a balloon payment, in case you're wondering. And that actually is why the world economy crashed. Basically, a bunch of people had this same linear model in mind of the trend line goes up, and they just assumed it was going to go up forever. It was just going to keep going up, and it didn't. And that ended up being really bad. A lot of people lost a lot of money all at the same time, and that caused a variety of other things to happen. It's not an economics class, but it caused a bunch of stuff to happen, basically. When I say a lot of people lost a lot of money, I don't just mean individual investors. I mean like large banks that had bought a lot of these, or that had sort of invested in this same sort of thing a lot themselves. So anyway, the trend did not continue, is the point I'm attempting to make in perhaps the longest way possible. The trend did not continue because with time as your independent variable, you never know what's coming up in the future, right? You can only predict based on the past, and the future performance or past results are not necessarily indicative of future results. And a lot of people kind of forgot that. And a lot of bad stuff happened for quite a few years, actually, about 4 or 5 years before we had a full recovery. Anyway, that's the point I'm trying to make. That's extrapolation, by the way. Extrapolation is when you guess outside, you use your model to predict outside of the range of data that you have. And so if somebody, so this is based on, this prediction here for final exam scores is based on midterm averages that are between 40 something and 90 something. And so outside of that, I don't feel very good about the predictions that the model gives. So let's see how to actually find a prediction based on the model. I'll show you two different ways in the calculator. And then we'll go, then we'll learn about outliers and then how to do this in other formats as well. So here's how you can actually make a prediction. So let me go back to the notes real quick. So I'm going to make predictions for these scores, for these midterm averages. Somebody who got a 67 average, somebody who got a 99 average, and somebody who got a 12 average. So yeah, first let's see how to do that. I'll show you the easiest way to do it, and then I'll show you an alternative way, just to emphasize something. So the easiest way I know of is the following. I'm going to go to table. Second function of graph here is table. So let's go there. And what you'll notice is that it's got x and y1. And remember that my regression equation is in y1, right? If I go to y equals, that's where the regression equation is. So what this table is doing, it's actually making a giant XY chart for you, right? It's putting in all these X's and giving you out all these Y's. So I wanted to do 12, 67, and 99. And if I wanted to, I could just scroll down to 12, right? There's 12, our prediction is 17.772. I could also scroll down to 67 and 99. As you can guess, that's going to take a little while. There's a better way, and that is if you go to table set, which is the second function of, where is it, of window here. So right there, we can turn independent, which is the X variable, to ask, which is what I'm going to do. What this means is that the calculator will ask you for the independent variable, and it will tell you what the dependent variable is. And you might say to yourself, well, we could also make the dependent variable ask. Don't, it's dumb. You can if you want to, it just doesn't do anything really. Yeah, feel free to try it, but leave it on auto in general. So table. So notice it's blank now because it is asking us to put it in an X value, like for instance, 12. And then we'll tell us what the output is. So what it's doing here is it's taking this and putting this X into the function that we put in Y1 and telling us what the Y is. So I can also do that for, say, 67 and 99, which were the things that I wanted. And so it gives us predicted final exam scores for midterm averages of these numbers, right? And so if someone had a midterm average of 12, this predicts, or our model predicts, that they will have a final exam score of 17.77, or about 18%. Similarly, for 67, for an X value of 67, so midterm exam average of 67, it outputs about a 70% on the final, and same thing, 99 goes to about 100. So the question about interpolation versus extrapolation is, which of these do we feel good about? Which do we feel bad about? Which do we feel somewhat okay about? And why? And the answer to that is based on what our model was based on. So our model is based on data that is between, it goes up to 96 was about the highest, I think, and then the lowest was like 48 or something. All right, we can look through the list. 42 maybe here. So let's go to the graph and then trace, and then go to the left here. Right, that's 43. Yeah, this I saw 42 in the list. So this far left one must be 42. So the lowest X value we had was 42. So I feel pretty good about our model for people who scored between 42 and 96 on the midterms, or had those midterm averages. And the reason I don't necessarily feel very good about things that are much above or below that, well, above, you can't really get much higher average than 96 on the midterms, right? You could average 100. I do give extra credit, so you could average a little bit over 100. So I guess, somebody could theoretically have a midterm average of like 105 and be off this chart. It's also pretty easy to have a midterm average of lower than 42. Now, most people who have an average of something under the 40s, the midterm average in like the 20s, or in my example here, 12, it's not because they gave it their best shot each time and it just didn't work out, right? Like that's usually not what happens. Usually what ends up happening is the reason somebody has a 12 average on their midterms is probably because they like missed 2 of them, right? There were 3 midterms, they only took 1, did bad, and then missed the other 2. That's how you get a 12 average. So what that means is somebody who has done that is very different than someone who has an average, in here, who got a 76 average, right? To get a 76 average, you probably got, B's and C's on the midterms, right? Or maybe you got, 1 good one, 1 A, and then like a D, and then a C, right? Something like that to get a 76 average. But this is probably somebody who was taking all the midterms, giving it their best shot on each one. And so when they do that again on the final, we would expect the results to be about the same. Whereas somebody who has a 12 average probably gave it their best shot on midterm 1, didn't show up to midterm 2 or 3, got zeros on both of them, and then came to the final for some reason to take it. And so I would not expect how they do on the final to be well predicted by all of these other people who are qualitatively different than that person who got 2 zeros, right? And you can see that in the fact that 12 is way outside this, way outside the box here, right? Our low is 42, so 12 is way outside of that. And so I am not at all confident that this model will do a good job of predicting how somebody like that, or somebody in that circumstance, I should say, would do on the final exam, right? If somebody did bad on 1 midterm, missed 2 of them, and then showed up for the final, it probably means that they're going to try and make a last-ditch effort and have been studying really hard. And so I would expect that person probably ends up doing way better than 18% on the final. It's not to say that it's a great idea to try that, but yeah. So I just don't think that somebody who has a 12 average is qualitatively similar or quantitatively similar to the people who are in this chart. And so since the model was derived from the people who are in this chart, I wouldn't necessarily expect it to do a good job of predicting how someone who is not like these people would do on the final. And so in a qualitative sense, it makes sense that their Y value would be different than we would expect based on just midterm average. And the fact that they're quantitatively, it also makes sense because they're well outside our range of data. So big extrapolation, I'm not expecting that prediction to pan out very well. So the other 2 choices were 67 and 99. 67 is like right in the middle here, right? So it's in this vicinity, right? Here's 76, and there's another 76, and there's a 48 and a 57, right? You can see 67 is going to be like right around here, right? The very middle of our model. I'm feeling pretty good about that prediction. Now, there's actually a fair amount of variance in the model around here, mostly due to this one person, maybe these 2 people. But basically, that is like the very center of our data. That's where I feel the best about our prediction, right? So our prediction of 67, which ended up being like the prediction was like 70%, I would feel reasonably confident about that, right? Somebody who has a 67 average, I would expect that they're probably going to do generally near 70, right? Maybe a little higher, maybe a little lower, depends on the person, depends on the day, etc. But I feel pretty good about 70 as a reasonable prediction. Somebody who scored 99 was the other one. Well, our high value was this one, and it's a 96. 99 is bigger than this, but it's pretty close, right? It's only 3 points bigger than this. So I'm reasonably confident about that prediction as well. Also, somebody who gets a 99 average on the midterms is probably pretty qualitatively similar to somebody who gets a 96 average on the midterm, right? Both people are getting basically everything right. And so I would expect that the prediction would work reasonably well for that person. I'm a little bit less confident than I am about someone right in the middle range here, but still feeling reasonable about that prediction. Like very slightly outside of our range of X values is okay. Small extrapolation is generally all right and kind of what you want to do some of the time anyway. So that's how I'm feeling about those answers, or about those predictions, right? 67, I'm thinking that the 70% we predicted is probably pretty good. 99, the 100 that we ended up predicting, I'm a little bit less confident about it than about the 67, but still feeling pretty good. This 12, I don't think this is a good model for that, right? I would really want to have a bunch of, if I wanted to try and predict how this person was going to do on the final, I would want to get a data set of people who had averages around this number and then make a separate model entirely for it. So what range of midterm averages do you think would be reasonable to predict final exam scores for? In general, about the range should about equal what you have data for, and not much outside of it. A couple points outside is probably all right, but in general, stay inside. The last thing, and I know this video has been really long, maybe should have broken it up into two, but a little late now. Last thing I want to talk about is outliers. So in the past, we have generally defined outliers by how well we use the 1.5 times IQR method, which sort of measures how far outside of the middle 50% of data a point is, and if it's far enough away from that middle range of data, we consider it an outlier. Now, I mentioned at the time that there was another standard way of doing outliers, which is my preferred way, to be honest, which is the 2S method, or 2 sigma method. I guess 2S for us. Which is the reason I like it is the following. Here's the idea. What we're thinking of when we do regression, there's an inherent assumption that I didn't talk about, but that assumption is that your residuals, remember how far away each point is from the line, are normally distributed. That's actually a pretty reasonable assumption a lot of the time. And in fact, let's do this. Let's go to calculator, and remember that we found our residuals earlier, right? They're in L3 over here, and we can test to see if these are normally distributed. So let's by making a QQ plot, right? That's how we do that test. So let's do that. Let's go to stat plot. Number 2 is going to be a QQ plot, and we're going to make it of L3. Data list is L3. Everything else is fine. Now, here's why I always go to y equals, by the way. I'm going to go to y equals and turn everything else off. I'm going to turn plot 2 on and everything else off so it's not all cluttered. I'm going to go graph, and it's not going to show us anything because we're going to need to zoom stat. And we get that, right? So there's our QQ plot. That's pretty straight, right? This is about as straight as where we're going to see for a QQ plot. It's actually a little bit kind of funny in the middle. Right, it's a little bit wiggly in the middle, but not too bad, right? It's not exactly all over the place. It's still pretty all clustered together. And so it's reasonable to think that these residuals are normally distributed. That these residuals right here are normally distributed, which is what you want. In general, do I want to give a history? All right, little history lesson. Another tangent in this video. Just what this video needed is another tangent. The way normal distributions were originally discovered is that astronomers, way back when telescopes were not as precise as they are now, right? They were all made by hand and aimed by hand and all that. They needed a consistent way to, whoops, what did I just do? Sorry, I touched my screen. They needed a consistent way to agree on the position of a star, right? Because they're measuring everything by hand, and you would have 2 people on the same night, like literally right next to each other, looking at the same star and getting very slightly different measurements for it. And so all of these errors, right, were deviations from what the actual position was. There was always a little bit of a deviation in one direction or another. And so in attempting to map this, or attempting to figure out how, what data is trustable, they ended up contributing significantly to statistics, because that's where normal distributions came in. In general, normal distributions are errors around a central value. So errors that are, if random errors around a central value are normally distributed, and that's actually where normal distributions were discovered. So if you have a central expected value with random deviations around it, what you get is a normal distribution. And so that's what we're checking here, right? These things right here are our deviations from our predictions. Our expected values are on the line. And these are the random deviations away from that line. And so if when we do a QQ plot, we get that they are not normally distributed, that's potentially a problem, right? Because it's saying that there is some pattern that we're not detecting there. These were, and so we're pretty happy about that, and we don't necessarily think there's a problem. With that in mind, let's go back to the notes. So that's what this picture's out of the book, by the way, is showing, is that for any given X value, there is a normal distribution kind of laid on top of it of where we would expect to see points, where we'd expect to see the points. So you can think of it as like a separate normal distribution for every X value, but that distribution has the same standard deviation everywhere, and it's just the mean is the line. What am I trying to say here? So the reason I bring all that up, one, to kind of just explain it in general, but two, to explain why we are using a different method of determining outliers. Since we're assuming that there is normally distributed deviation from our line, the thing that makes the most sense to use to determine outliers is something that goes with a hypothesis test, right? The hypothesis test that we use for normal distributions, just to say that we would think of something as unusual, and unusual result in a hypothesis test would be if it was in the outer 5%, and a usual result would be within the middle 95%, right? 5%, that's where we're rejecting the null hypothesis. So data values out there would cause us to reject the null hypothesis. Inside the middle 95% would not cause us to reject the null hypothesis. And 95% is about 2 standard deviations. It's actually 1.96, as we know, but 2 is close enough. So a way to determine outliers, or to determine whether something is an outlier, is if it is more than 2s away from your mean. That is to say that it is more than 2 standard deviations away from the line. Right? So the line is what the mean is for each of the distributions. And so if something is more than 2s away from this line, that's where we're going to consider it to be an outlier. So let's go look at that. Let's go back to the calculator. And let's look at the graph here. Sorry, I'm going to go to y equals. I'm going to turn this back on, this off, and this on. Graph here. Can't really see anything, so we'll zoom stat. So what we're going to do is we're going to see which points are, if any, are at least 2s away from the line. Now you might say to yourself, well, how do we calculate s? The calculator does it for you. There's another reason we're using Linreg T Test. All right, so for the millionth time, we will go ahead and rerun this test. I think it's actually about the 4th or 5th time. And if we scroll down, or I guess at the bottom here, it is this, 8.96. That is the sample standard deviation of the points, of each of the points, if we take the line as the, what am I trying to say here? If we take the line as the mean, then the thing that we get is s equals 8.96, or about 9. I'm just going to call this 9 for our purposes. So outliers are going to be any point that has a residual, which is how far away it is from the line, that is bigger than 18, or bigger than 1.96 times 8.96, which I'm just going to call 2 times 9, which is 18. So anything that has a residual bigger than 18 or smaller than negative 18, just to say any point that is more than 18 above the line or below the line. We're going to call those things outliers. That's our definition of it. So I actually have two or 3 points. There's some points here, right? This one's kind of far from the line. This one's kind of far from the line. This one's kind of far from the line. This one's a little bit far. It's probably not 18 though. So we're just gonna go look through the list and try and find anything that's got a residual of 18 or more or negative 18 or less. So that's how we're gonna find our outliers. Where are we at here? 18. Oh, I missed the big one there, right? Negative 25, that's more than 18 below. Do we have anything above? Yes, 18, a little bit more than 18 above here. So this person's person number 17, and then person number, I don't know what number they were, 7 or something, 6. So person number 6 and person number 17, 18, 17. So let's go see what they look like. I think those are the two that I highlighted, right? So 6, that's person number 6, right? They scored 73, that's midterm average of 73, and then so we thought they were going to get 75 or 76 or whatever on the final, and they actually got a 50, which is really bad. And then was it that person? Yeah, then this person, who they had a 57 average on the midterms, and so we thought they were going to score about a 60 on the final, and they actually got a 79. So good for them. And so those are our two outliers, and you can see that they are the farthest away, and there weren't any others in the list. So that's all outliers are. They're things they're points that are far away from the line, which is to say they have big residuals, either very positive or very negative residuals. And what we mean by big is more than 2 standard deviations away from the line. And the way you can find the standard deviation is doing Linreg T Test. It's one of the things it finds for you. Might as well run it one more time. Right, and gives it to you right there. It's S. Notice it's giving you S instead of sigma because we don't know sigma, right? We only know S because everything was derived from the data and all the data was from the sample. So everything here is a statistic. That's why we're using all English letters. A, B, S, R, and R squared are all English / American / I don't know the origin of these. But not Greek is what I'm trying to say, right? And so there's Greek ones that go with this: alpha, beta, sigma, and rho. All right, let's flip back to the notes, do a little bit of a wrap up, and call it good. Okay. So we did all this stuff, right? We made a normal probability plot, found any outliers, etc. Now, from here, I gave you a bunch of questions to do. These are totally optional, not graded, just for your practice, because we don't necessarily have. This is the last topic, and so we have less time to practice on this than other topics, and less time for you to ask questions. So I figured I'd give you more stuff to do in case you want more practice. So yeah, here I'll scroll through these. I stole some of these from another teacher. Stole some of these from a book. Made up a couple. The one that is most like a question that I would ask on a test is number 6 here. This is quite similar to a question that I might ask on a test. So have a look at it. I'm not going to go over it here. This video is more than long enough already. But yeah, that's kind of what I want to say about regression. Now, there's actually a lot more to say about regression. We didn't talk about other kinds of regression, polynomial regression, exponential regression, etc. If you ever have to learn about that stuff, it's actually quite similar to linear. You're just using a different kind of function, right? So instead of graphing with a line, you're graphing with some sort of curve. And then the more interesting one that we're also not going to do is multiple regression, where you use more than one x value. You're using a more than one explanatory variable, which is kind of to predict a response variable, which is kind of more how the world actually works, right? Usually things are not predicted, one thing is not predicted by only one other thing. And test scores is a good example, right? Like if I was going to do this, I might actually want to do midterm average, homework average, which I've told you in the past actually doesn't correlate. So that's actually one we wouldn't want to use, but as an initial attempt, I might want to use midterm average, homework average, how much sleep the person got the night before, any number of other things. I can't think of anything off the top of my head right now, but there are a few other things that go into predicting how well someone's going to do on the final exam. than just how they did on the midterm. And multiple regression allows you to do that. It's actually pretty interesting. It's also beyond the level of the class a little bit, because it deals with higher dimensional spaces, which we're not going to worry about. But anyway, there's a lot more you can do with this, and I feel like if you ever have to do any of that, this will be a good baseline to start from. So check out the summary, go through the notes, try all the homework problems. If you have any questions, and by gosh, I expect you to, feel free to come to the Wednesday or Saturday discussion sections, and we have another week that's just practice time for regression as well, or for anything you want for the final or for the third test and the final, but specifically, you will know about regression and can practice it during that time. So with that, I think I'm going to end this very long video. This has to be the longest video in the entire class. So yeah, I maybe should have broken this up into two. But anyway, I would say that I will see you in the next video, but I don't think there's going to be a next one. I guess I'll make a video. I guess I'll make one for the homework and for the final review. Yeah, for the final exam review, or not the final exam, but for the third test review. So I'll see you in those videos. But other than that, good job getting through all the material, and keep it up, and I'm sure you'll do well. All right, I'm gonna end the video. That's not the right button.